Go ahead.
Thanks, Henry. So thank you for joining us for our torque calibration errors webinar today. My name is Heather Sando, and I'm the marketing manager at Morehouse Instrument Company. I'm going to be assisting throughout the webinar today, so if you have any questions, please enter them into the chat. I've also muted all the phone lines just to eliminate any background noise during the presentation. So while we still have a few people I see joining, I'm going to take a few minutes just to give some background information on Morehouse Instrument Company and what we do. So we're a manufacturing company that produces force calibration equipment and torque adapters that are used around the world to measure force and torque. In 2020, we celebrated 100 years in business. So we're in the risk reduction business for force and torque calibration. We often have hard discussions with customers who are maybe confused or frustrated or don't know about the importance of their measurements. So in our calibration laboratory, we have two labs, a force lab and a torque lab, at very high levels of accuracy. For torque, which we're addressing today, I'll talk about that first. We have the second most accurate torque standard in the world, which we actually purchased from the National Physical Laboratory in England. We have uncertainties of better than 25 parts per million. For force, we are a primary standard laboratory and offer deadweight calibrations up to 120,000 pounds of force, known to within 0.002% of applied force. And we also have force calibrations up to 2.25 million pounds, or 10 meganewton of force, known to within 0.01% of applied force. So today our presenter is Henry Zumbrun, who's been the president of Morehouse since 2013 and worked at Morehouse for more than 20 years. Henry really has a passion for measurement accuracy and reducing risk associated with measurements that impact safety in our day-to-day lives. One thing I've learned from Henry is just about the far-reaching impact of force measurements on the planes we fly in, the bridges we ride on, and the cars we drive in. So at the end of the day, we know we've done our job here at Morehouse if we can help someone improve their measurements to make the world a safer place. And that is our purpose, to create a safer world by helping companies improve their force and torque measurements. So today we're presenting this webinar just to help educate on what really matters most. So now I'm going to pass it back over to Henry.
All right. Thank you, Heather. So final seconds on closing the poll. As Heather said, we are really in the risk reduction business, but we're also in the solution business. So if you ever want to reach out, we all believe in helping others. And if you ever want to reach out with common problems, we don't sell torque wrenches, but if you want to talk, have a call about back torque, I'm willing to talk to you. So again, it's just really anything we can do to help make the world a safer place, we want to do it. And of course, we figure through that, people will eventually buy and purchase products from us, and then we can do right on both sides because we stand 100% behind our products, and we think we have some of the best solutions out there. That being said, there are many other people, and we appreciate your time today to listen to it. And hopefully, I always say, if you can take away a couple tools in your tool belt that can make you better or make your process better, we've done our job as far as these webinars are concerned. So that said, I'm going to close the poll in 20 seconds after I read this. I encourage everybody else to, answer the poll. There's still, 23 people with a no answer. So outcome from today, the participant will understand metrological traceability for torque and be able to have knowledgeable discussions about the types of torque standards and torque measurement errors. So what is torque? It's derived from the SI base units of, here we say, length, force, which is mass times acceleration. So we're in length, mass, and time, and those are the base units. And if we want to get very technical here, we can say what those, the meter has a definition, the definition is there. And then the kilogram, which is interesting, is because it was redefined. It was redefined in 2019. Used to be, it was the last intrinsic standard where they had an artifact and all the artifacts were compared. And they were trying to redefine it for so long when they were talking about Avogadro's versus Planck. They ended up with Planck's constant, and there's the agreed upon value. And then he agreed upon it with researchers able to make precise mass measurement using equipment such as a kibble balance. And they have a sphere, and they're still in that process of, you know, cleaning. I think the Australians are making the sphere. Really cool stuff. If you're into YouTube, I know if you have kids, they're probably into YouTube. Really cool stuff to look up the kilogram and the sphere. You know, it's something that's really, really interesting. And then there's the definition of the second. So there's the really for the metrology, how these are defined. We're just dealing with length times and mass. And for that, I now am closing the poll with 22 no answers. So everybody, hopefully, if we're doing well, can it says 15 seconds left. So with that, hopefully 15 seconds, we'll share those results. Definition of torque, also called a moment or moment of force, is the tendency of a force to rotate an object about an axis, fulcrum or pivot. Just as force is push or pull, sometimes we think of torque can be thought of twist. I started to think of, you know, Chubby Checker and all his songs, Let's Twist Again, the twist, all that. However, yeah, when you think about it, it's force times length. And fortunately, we happen to know an excellent cartoonist. If people do not know who this person is, I highly suggest you search Ted Green. Just does fantastic work. And here I said, this is a peeve of mine. And here we're talking about something that people get wrong. And all the wrenches, all the manufacturers of wrenches, they always get Newton meter right. You look on a wrench, none of the wrenches say meter Newton, but they say foot pound instead of pound foot. And so we had Ted make us this kind of funny drawing here. It's still in draft. I'm hoping we get a cubit put in the one guy's pocket, just for like a little bit of an Easter egg on those that follow metrology and the cubit, which was used to measure length. But foot pound, it's very important here. Foot pound is a unit of work or energy. It is the energy transferred upon applying a force of 1 pound force through a linear displacement of 1 foot. The corresponding SI unit is the joule. So when we talk about foot pound, we're talking about the SI unit of the joule. A pound foot is a unit of torque representing 1 pound of force acting at a perpendicular distance of 1 foot from a pivot point. Very different definitions. I know some people say, you know, who cares, whatever. However, it's important. It's again, make sure we're all speaking the same definitions and everything else, and hopefully you get a chuckle out of that cartoon there. So talking about primary standards, this is where we're going to take some time and just explain some of them, explain some of the errors. You know, this is how typically if you're just doing wrenches, that torsion cell has to be calibrated somewhere. Is it calibrated with arms, weights? Is it calibrated by transfer? All of this stuff. The most common way to do this is the lever deadweight systems, and it consists of a set of calibrated masses that act on a calibrated lever arm, and it can be directly applied to the transducer in the case of an unsupported calibration beam. Now, a lot of people unsupport the arm, and we'll talk about some of the pitfalls to that and what you may do to quantify the errors in your system, because it is a lot more than, you know, here, it is a lot more than force times length here on the system. So the ideal case, here's a system. This is actually at PTB, which is a National Metrology Institute. They're in Germany. They have the best torque standards in the world. Really just premier, awesome lab, awesome technicians, and awesome scientists that are there. And they're doing some just really fantastic work. But here's the picture. In the ideal case, we're going to have a lever arm will be connected to a bearing to eliminate bending from the weights and masses and to minimize friction. This type of system is used for static torque calibration, and there's some standards, the DIN 51309, BS 7882, that's the British standard. And in this country, some people may not know about it, but it did come out in 2015. We have ASTM E2428. What's interesting about the ASTM standard as being part of that committee, part of the E28 committee, is we did a round robin, and we did an ILC when we sent a standard to PTB. They calibrated it, and then we all calibrated our systems. And PTB has torque values. They know them to within 10 parts per million. And Heather said here, we know ours within 25 parts. Our torque standard is the second most accurate system in the world, the first most accurate in North America, and not many people are even close after that. So PTB definitely has the best capability. We're cool having second best. We're more than fine with that. Though what this proficiency test really did for us is to say, hey, PTB did this torsion cell, we did this, and everything is passing and good. And the rest of the committee, a lot of people in the committee did it following this new method, and we had some outliers. Went back and they redid some cows, and they were able to take those answers from PTB, and they were able to tune in their system. They were able to say, hey, I'm claiming way too low uncertainties here, or hey, I have some friction problems, maybe I should support my arm. Really just interesting things. So again, with the lever dead weight, these typically tend to be chain loading, which means you pick up one weight and then you have to pick up another weight. Some consist of multiple weight stacks, various weight or multiple weight stacks of the same size. And then if we start going over, their systems are typically used for two different types of torque arms, single-ended and dual radius. Torque is generally generated by the application of a known force at a known radius from the center of rotation of the torque transducer. And when people design the radius beams, the manufacturers, they are typically designed with a plus or minus 8-degree usable arc, which within which the calibration accuracy is unaffected, because that arm's going to bend, right? It's going to bend, and you have the arc to make sure your distance and everything is the same. Single-ended beams do not have a constant overturning moment as the dual radius arm would have, and may have additional error compared to radius-ended beams. We see a lot of single-ended beams. In fact, so much that when we teach this class, now and then, we have a single-ended beam that we take down, and we have known weights, and we can show there's a significant error source compared with single when you can compare single to dual. Single-ended are much less accurate and carry a much higher uncertainty. So when we actually do that type of demonstration, you get to see it, and it's quite large. So if you're in the market or looking for arms, I always recommend dual-ended. Here's an electronic transfer standard. This is at PTB. This is a pretty awesome transfer standard. So the story is that the company that builds these, they build a lot of them, and to get the accuracy, they just build them and test them. So there's still some trial and error, and that they throw out a lot of these transfer type standards because they don't meet. Now, if you send a torsion cell to PTB and you do not specify dead weight, chances are they will use a transfer that was calibrated in dead weight, and that is around 0.02%. So 20 times the dead weight. So you really want to, if you do that and you get into it, you get to your PTs. And if you are sending something to, say, Morehouse, where we can say, hey, you want to know if your system's good or not good, you send us a torsion cell, we do it, you bring it back, you have the answer, and then you put it in your system, you can do an inter-laboratory comparison. The important parts about those comparisons is to make sure you have the conversation, ideally with contract review, under how you're going to bolt this down. If you have a load cell or you have a torsion cell that needs bolted, loose versus tight bolting makes a big difference. So that's something you really want to do. You really want to quantify. The easiest thing to do is to tell the lab, hey, bolt these down to 10 Newton meters, 20 Newton meters. And then you can follow the process and everybody can align everything. Another reference type of torque transducer you can see here is torque is applied using a motor or hydraulics, with the torque controlled by means of a calibrated reference torque transducer and a feedback loop. Other similar designs may take traceability from calibrated load cells, measuring the reaction force at the end of a lever arm. That's something, we sell a lot of load cells. Some of the customers will have us calibrate load cells and force, and then they'll use their lever arm. They can be used to measure static torque, but has an advantage of being suitable for continuous torque calibration, whereby the applied torque is applied over a much shorter time. And then a disadvantage is that the uncertainty of applied torque will be much higher because the system is dependent on the prior calibration of the reference. So with that, we have, I'm going to try here. I believe we have a new polling question, if I can get it loaded here. And we have a new polling question here that everybody should see that says the following. What types of torque calibrations do you currently do? Torque wrenches?
Yep, Henry, that was the first one. That was the first one that they answered.
Oh, so Oh, we had that.
So they
one.
already answered that one.
Okay, thanks, Heather. So we had that,
Yep.
the results were there. Okay, cool. Sorry that, thanks for Heather. Still getting the new system. So I believe why everybody's here is this section. And this section is sources of potential measurement error. And here they are. They are using mass weights instead of force weights, calibrating beam deflection and temperature, misalignment load position, warm drives on the beam or transducer, introduction of bending and parasitic effects, bending forces on an unsupported beam, those are unavoidable, and temperature effects on the torque cell cable. So I have launched the other polling question. We're going to get to that later. If you want to answer it now, you're more than willing to, I encourage people to answer it. If not, you can wait till the polling question. So we're going to talk about these errors. One easy error is using mass weights instead of force weights. And it is very important that the gravitational value for the calibration laboratory is established. The effect of not doing this could be a variation in the force produced by weight of perhaps 0.1% or more of reading. So it is strongly recommended that you establish the local value of gravity for your laboratory and use weights that have been calibrated at that gravitational constant. The thing here is, if you're using mass weights, they're not adjusted for gravity. They're not adjusted for air buoyancy, and they're not adjusted for air density. So you really need to correct them for force. We're going to go over ways to do that, but the ideal solution is have someone come on site and have a National Geological Survey Agency do it. There's other ways, and the other ways are like to go to NOAA online. And if you go to online, I have a slide here I'm going to show you right now. If you go online and just use NOAA, this may be more than good enough. And it's the expanded uncertainty from this calculation is likely to be within 5 parts per million anywhere in the U.S. It doesn't work outside of the U.S. It works a little bit in Canada, but not too far past North America. The uncertainty value as the maximum or the actual reported value belongs in any uncertainty budget for pressure, etc., as described. This one's for torque, so torque budget. Of course, the mean value of G reported must also be applied to the actual measurement data as a correction. So you can use mass and correct, you just have to do it, and you have to know your error sources. You can also hire survey firms, they're going to get you within a half a milligal. Even though the daily changes in G can be averaged by a survey, a single calibration of measurement of customer will not take these daily changes into account. The phase of the moon can affect your gravity. It's so minimal for a lot of these measurements that it doesn't matter. And really give credit here, Philip Stein, I encourage anybody to go seek out this paper. It's called The Gravity of the Situation. Philip Stein was just a great metrologist, wrote the CCC primer and a lot of other things. Just really, really good. So the weights, I said it, weights used for torque, force, even pressure, they must be corrected for local gravity, varies by up to 0.2% across the US. The additional notes, the elevation of each weight should be considered. If you had a really large stack, chances are no one's doing super large torque with a lot of weight, because we'd all hear about it if somebody could do, 500,000 pound-feet. Material density, knowing the density of the material from which the weights were manufactured. That goes into the equation, which I'm going to show you. Buoyancy, the Archimedes principle applies. Air pressure under the weights causes an upward force. This reduces the effective force generated by the weights, and therefore the mass must be increased to allow this. When used in air, the correction is approximately about 0.012%. So if you're following, you got some serious errors here. If you're using mass weights and you're not correcting for gravity, you don't know the material density, and then air buoyancy on top of it. So if we're looking at this, here's a real takeaway. If you are using mass weights and want to get a little better, you can do this. And this is converting, force to mass, the corrected method. And you can see it. You can use the formula to convert mass to force. But if you find the location of the measurement, you can go to GeoPlanner. That will give you your longitude and latitude. And then you go to that NOAA site, which I referenced, that predicts your gravity. So if we were to say here, find the air density and material density for, for Denver, we could go look up where Denver is, and I added some things for material density, assuming stainless steel and whatnot, and I did the formula. So a mass equals force, and there's also a formula for, again, for force. You can just, redo this formula, or we have it on our website. So use that formula. And so if we did what this is essentially showing is that if we did a calibration here in force, sent that device to Denver, and they wanted to convert it back to mass for, like, say, weighing, here's the formula. It means really that in Denver, you read it two ways. In Denver, to generate 10,000 pounds of force, they would need their mass adjusted to 10,011.89 pounds. If we did the calibration here, send it to Denver, that would equate to that. So you can read it both ways. The weight handling, this is a known error. The physical lifting of weights onto a platform creates additional error. The error is due to uncontrolled application of the weight onto the pan. Handling weights and placing them onto a pan may cause vibration error, tape misalignment error, and introduce a pendulum or swinging effect. If some of the arms have a twisted cable, the weights could sit there and just turn in air. So recommendation here, it's a harder recommendation to fix and gets more expensive, but to minimize it, if you're concerned with it, is use a fixed chain loaded or pneumatic weight stack in which the weights can be applied as uniformly as possible. Kind of like our Deadweight systems, we can build those for torque if need be. So calibration beam, deflection, and temperature. I sat through this long conversation at National Institute of Standards Technology. The person gave an excellent presentation on torque and torque error. And at the end of the day, I was like, wow. I talked to people. I said, wow, that was really a great presentation. At the end of the day, one person in the class said, you know that guy, his lab isn't even controlled to within plus or minus 7 degrees C, which just completely deflated almost everything that the person said, because that's huge error. As that temperature changes, the length changes. So the material the beam is made of will determine the appropriate amount of weight that can be supported by the beam. People tend to do this. They want to use a big beam and go lighter. They don't want to, do the temperature. Using more weight than the beam is designed for may cause significant deflection. Not good. The properties of material of the beam will expand and contract, changing the length of the beam. That's a temperature error right there. And then the temperature effect can be minimalized by maintaining the room temperature of the calibration laboratory at the same temperature the beam was calibrated. So if you have a beam that was calibrated at 20 degrees C, probably should maintain your lab to plus or minus 1 degree C, if not better. And all that depends on what type of uncertainty or uncertainty you want to claim. So here, misalignment. Here's some examples of misalignment. You're trying to line everything up. It's almost impossible. No system is perfect. So it's not uncommon for the errors from misalignment to raise the combined uncertainty by more than 10%. That's a huge number. That's like you're really getting things wrong. But would you know? The question is, would you know if you had that error unless you're sending a cell to PTB, sending a cell to Morehouse, and bringing it back and doing your own ILC? That's a hard one. A lot of people don't close the loop. They just say, I have this known force, I have this known length, I'm good. That's not the case, and we're going to show you more examples of that. But if we misalign something over 1%, I did this in a class where we did our machine, and we misaligned our machine, like deliberately misaligned tapes and everything else. Your misalignment error can raise the uncertainty by like tenfold. And we had something where the combined uncertainty of the cell during the E2428 cal at full scale was about 0.003. You misalignment and it jumped to 0.03. So like, still low numbers. A lot of people are out there saying 0.03 at the end result of a wrench is like 1%, 4%. Still really low numbers. However, that increases your risk and your measurement traceability, depending on who's doing the cal. Maybe the one lab misaligns the cell. They think they're operating at, these really low uncertainties. They're actually 10 times higher. Then they do another transfer standard that then is used for the wrenches. All of a sudden, you could start eating up large error sources, especially when you get into these different types of misalignment. But again, it's difficult to align. Usually there's some mismatch of the two axes, and one way to minimize this is using flexible couplings. They get expensive, but until you start doing any of this, I recommend figure out if you have the problem. Do that interlaboratory comparison. Another one, square drives. Square drives are fine, but the fit and rigidity of the mounting plate are important. The more you use a square drive, the more it wears. This is why, like, I'll show you, we designed something with a hexagonal drive. Still will wear. Hexagonal's great. It'll still wear, but it won't wear as fast because you have 6 surfaces instead of 4. But if the fittings are worn, the proper torque will not be generated. They'll be loose, they'll be slack. It's not uncommon for this error to exceed 10%. Another big, huge error. So a 10% error is going to, on a what, again, you calibrate the cell, you go for a wrench, a 10% error is going to be huge. You're not going to get the wrench in. So, and then we're talking of bending and parasitic effects. The influence of bending and parasitic effects on the transducer will be dependent on the design of the transducer. Not all transducers are made the same. However, the reproducibility of the device when calibrated in different orientations can often be a good indication of influence in bending. So you have that square drive, you put it in your machine, you put the arm on, you put weights on it, you get a number. That's probably all you're doing. If you're doing more than that, that's great. If you want to test this, rotate that cell 90 degrees, rotate that square drive and try and see how good it is, right? That's what we're saying about calibrating in a different orientation. Do more than one run on it. Get your numbers. Ideally, you probably do two runs with it at the same spot to get repeatability numbers, and then start putting it in a different orientation and seeing if it repeats. If it doesn't repeat, you could have some additional bending. And next, we're going to talk about bending forces on an unsupported beam, which are really, really common. And NPL did this awesome study with Norbar, and they wrote a paper, and this is what came up to it. This is what came from it. And here we have an unsupported beam. You see the weights, you see the transducer. They say, be aware of the influence that bending can have on the measurement result and quantify it if possible. Again, transducer should be held rigidly on the mounting plate. The fit of the squares should be as good as possible to minimize any slack. And here's what they did. They took 3 beams and 3 transducers, and they have a transducer ABC, 2 kilonewton meter calibrated with a 1.5 kilonewton meter unsupported beam, a 2 newton meter calibrated with a 0.5 kilonewton meter unsupported beam, a 1 kilonewton meter transducer calibrated with a 1 kilonewton meter unsupported beam. And you can see the applied torque, and you can see the deviations. So what are they doing? Their relative deviation of transducers A, B, and C calibrated with Norbar unsupported beam, and they use the NPL reference, the machine that's at Morehouse right now they used. When NPL had it, the machine was good to 18.3 parts per million. A little bit better than us. We have to account for additional errors with different uncertainty components with accreditation. So they did this, and here's the data. I mean, the data on A, the 2 kilonewton transducer calibrated with a 1.5 kilonewton unsupported beam, you can see the error 0.02. This is just comparison. The best they were getting on this device was like 0.02. A lot of people here are claiming like 0.16, 0.12. I see a lot of scopes where they're claiming this, but this case, Norbar makes fantastic arms, and this case shows an error of 0.02. But hey, let's look at the other beams. So when we took, 200 newton meter transducer calibrated, and you look at these errors, these are all the applied torque. Look how high those errors are, and that's just from the weight of the beam. And we're going to dissect that a little more. So transducer B, 200 newton meter transducer was calibrated with a 1.5 kilonewton arm. 500 newton meter beam weighs about 16.6 kilograms. Look at these errors. So 500 newton meter beam calibrating a 200 newton meter transducer, and you can see as you approach capacity, they get better. But at those lower, points, say even, at your 20% point, the errors are really, really large. And this is what people don't realize. That's all bending. That's the weight of that beam. That's when we go back to the types of standards. It's where we're going with like supporting a beam takes a lot of this away. So now let's look at the weight of unsupported in relation to the capacity load cell has a significant effect on the transducer output. Now we're back to, back to that original. The worst affected region is 0 to 20%, where the weight of the beam is most significant in relation to the torque being measured. Under certain conditions, an unsupported beam achieves results within 0.02% of the reference value from the 20 to 100% range. And that was the transducer C, which is a 2 kilonewton meter shaft height. Now I've taken this and summed it up to just tell people, hey, your beam matters, and it matters quite a lot. So if you're using a heavy beam, you probably have these errors, and you probably need several different beams, and you probably need to have that test to see, back and forth. That's what they did. They used the NPL machine as the reference, and then they put them in these. What this led to, and you could say, hey, Norbar and NPL, this led to Norbar redoing a lot of their beams and making them lighter. So they're better than this now. But if you have the older beams and stuff like that, you could still have this. And really important, a lot of the manufacturers will specify like their torsion cells, what size beam to use with it. Now, how do we solve this? This setup is the best way. A bearing supported calibration beam, transducer adapters, flexible couplings, bearing. Much more expensive setup. So bearings are often used to support the beam and eliminate bending effects due to the weights of the lever beam and weights. Depending on its quality, the bearing itself may introduce errors such as friction, and the performance of the bearing still requires evaluation. So an air bearing, ceramic bearing, other bearings, you still need to go back and quantify them. Ceramics are pretty interesting. Air get to be expensive because you're doing that. You're running air into it. And if you can damage them rather easily if you don't have the air on and you turn them. They can get some scarring and some other things. So here is the poll. Hopefully people have answered it. So far we see not as many had answered it. Only 4 people had said yes. 82 had no answer here. So that's what we had. Unfortunate, but hopefully people are participating and looking at it. Morehouse torque arms. This is something we've been working on. I said about the hexagonal drives. This is a 0.5 meter long in each direction, about a 500 newton meter capacity. The whole Morehouse arm will weigh around 50 newtons. This is approximately half the weight, which means less bending. So less bending, less overhung moment. Our big hope is we're in the testing phase. Our big hope with these arms is that one of these arms can replace 2 or 3 of people's existing arms. So, calibration, sending it to, the dimensional lab on the CMM, however you get it calibrated, that's a big cost. So the hope is one arm can replace 2 or 3. So that's less standards, easier. We made this out of carbon. It's made out of carbon fiber. There's a little bit of steel there. So very low temperature coefficient for expansion. The steel's at the end of it. Hexagonal drive, which will take a lot longer to wear. It kind of stinks to change adapters, but at the same time, those 10% errors are quite large. So the arm components will be, carbon fiber, aircraft aluminum alloys, high strength stainless steel, boron, and epoxies. We're still working on the tapes and the stand right now. If you guys saw us at the NPL, we had the prototype, really cool looking arm here that is actually, it is built, it's in prototype, and we're doing final testing. Cross variable forces. This came, we were privileged to be able to present with Stahlville, very nice manufacturer. And this came from David Wan's slide deck that we can use it. And it's basically just showing like how the transducer reacts, how each type of transducer exhibits varying sensitivity to bending and cross forces. And there's a setup. You can see the various setup pictures there. And the summation of this is a web-style transducer greatly reduces sensitivities due to bending or side loading. We're just talking about that. The measurement is made much closer, reduced lever to the point where the reference and object are mated. And with this type of design, the Stahlville cells, very good load cells, very good torsion cells, Overloads up to 300% are possible without mechanical damage. The other thing that Stallville does that's interesting is it has a chip. It records exactly the life cycle of the cell and when it was taken to, say you have a 300 Newton meter cell. It'll record that it was taken to 330 Newton meters 3 days ago. It'll record if your technician took that to 600 Newton meters. You can go back and pull the log and say, this cell was taken. What about your Cal laboratory? It comes, if the Cal laboratory messes it up, it'll record it. So, I mean, eventually if it dies, it'll stop recording, but you'll know who did it and when they did it and by how much they did it. So really interesting technology that's buried in those and really good designs. So really on these, from as low as 10% of nominal, a web cell becomes desensitized to bending and side loading. That's why the recommendation here is really, towards those web type cells, if you can control what you're using for, the standard cells to calibrate the torque wrenches. Additional error here, temperature effect on wiring cables. If a cable is not wired for sense 6-wire, then switching signal cables will produce additional errors. That's something to look at in your meters. It's something we talk about. Same with load cells. Is several of these meters, there's a 4-wire cable. It introduces, so you have resistance of the cable. You're not feeding back the sense lines. An additional error based on the thermal coefficient of the material used and the use of different gauge wire and cable length. So if someone cuts a cable in half, or you have an oops moment in shipping where someone patches a cable, you could very much change the resistance depending on how much gets cut out and whatnot, which will change the output. And those errors can be high as well. They can be 0.1% or higher. Just depends on gauge factor, how long it is, the other stuff. The best takeaway here is if you're buying a new system, if you can buy, we have 4215 meters, Hattie indicators, our high accuracy digital. Meters, if you can buy a meter that is a 6-wire, you do not need to worry about this additional error. So if a load cell or torque cell only has 4 output wires, then the 2 additional wires can be wired plus sense to plus excitation and negative sense to negative excitation. So basically what we're saying here is any torsion cell, even if it only has 4 pins, it can be wired for 6-wire. Here's one where we get this question, or we've gotten this question a lot. Technicians talking about cosine error, what it means. A vector is a quantity that is defined by its size and direction. Every time the effect of a known force is evaluated on a static or dynamic system, all applied and resulting forces should be determined by both their magnitude and direction. If one says a 100-pound force is applied at point X on a table without fully defining the applied force direction, then an infinite number of solutions, each with its own set of results, can be generated. And I think it's easier, the next slide, I think this is easier for what we're saying. Length is 2 feet, force is 150. The effect of a known vector can be evaluated and expressed in various directions by calculating its representation in those directions. Different methods might be used for various coordinate systems such as the Cartesian, polar, cylindrical, and spherical. In most simplistic form, the applied force vector can be expressed in 2-dimensional flat plane in X and Y. And that's what we're showing here. So we really want this error to be at 90 degrees. I'm going to show an example, and this is a manufacturer that said, hey, this is a good way to measure force. Before this, there was no really good way to know to measure torque. Before this, there was really no good way, to know how the torque was. This is from their advertisement here. So they're showing this is a good way to measure torque, and we have a force of 150 pounds and a length of 2 feet. That's what we're assuming. This is the application. Since torque is force times length, simple math says 150 times 2, and that gives us 300 pound-feet, right? Not so much. What I was just describing on those other things is how you calculate that. So the above calculation can be true if the applied force is equal to 90 degrees. We go back to that other slide here. We're saying Fy, Fx, we want to set it to 90. If not, we can calculate it, though it's not going to be what we think it's going to be. And the force application plane is perfectly perpendicular to the pipe direction. So this would have been a good advertisement if we went to 90 degrees. Since we didn't, And if somebody does this and they think it's an accurate way to measure torque, we can calculate it. If we use simple X and Y planes, we can attempt to solve what it is. I don't know the angle here, but it looks like it's around 40 degrees as shown. Only a portion of the 150 pounds force generates torsion at the center of the pipe, and the rest of it is spent on pushing the pipe upward parallel to the wrench direction. That's what's happening. We're fighting that. So if we want to solve it, the torque generating force Fy will be, there it is, F sine A equals 150 sine 40 equals 96.42. And the force applied parallel to the wrench handle would be F equals F cosine A equals 150 times cosine 40 degrees equals 114.91. So we look at this, the generated torque at the center of the pipe is 96.42, and then the actual torque then is 96.42 times 2, right? And we're getting 192.84. People will have this in their slide deck, and they can use it. And these are pretty simple formulas. And if you look at it, if it would go to 90 degrees, as we said, we generate roughly 300 pound-feet of torque. There's going to be some errors because you have a change, but again, this is gross error. So if a manufacturer is out there saying this is a good way to measure torque, and a company is doing this, and they're passing things to the consumer, right here, they're testing pipe. So they're telling someone the pipe is good for torsion, but the actual error is 36%. Are you going to be comfortable using that pipe? How about if anybody's engineers in here on this call, if somebody gave you, hey, that passed, we applied it, that passed. In actuality, you have a 36% error. Is that going to affect your calculations, do you think? Are you going to want to, use equipment that's certified or calibrated this way? Again, this is the type of stuff in the metrology community that becomes a consumer risk that you later hear about somebody doing a recall or a loss of life event that gets traced back to this type of negligence. And we hardly ever hear about that negligence. So it's really important that people understand torque and how to calculate it properly. Okay, so errors and getting into calculating torque properly. Now we're going to discuss metrological traceability for torque. And what do we need to have in place to help ensure we are making traceable and meaningful measurements? And I have to say here, this can be applied to everything, right? Not only torque, it can be applied to force, pressure, whatever disciplines you're in, this can be applied. So we need to make sure the measurements are traceable. So what we're looking at here is first, we're looking at a chain. I like to call this the measurement traceability chain. We're looking at an unbroken chain of comparisons, and we're looking at measurement uncertainty, documented procedure, and the thing in the middle, that green, that measurement assurance holds everything into place. We're looking at technical competence, realization to SI units, and we're looking at periodic calibration. And this section goes pretty quick, but it's good to point this out. So traceability, property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So if you start with Morehouse, we calibrate your device, our machine's 0.025%, you have to absorb our uncertainty. Then if you use your torsion cell to calibrate another torsion cell, you do all the stuff. You calculate your measurement uncertainty in accordance with IOAC P14, AD guidelines, everything else. The important thing is you cannot have an uncertainty better than what we have. And then it's just going to keep getting propagated and larger and larger. So there is no torque traceability to NIST. NIST does not do torque. NIST does force and length. They do not do torque. So you don't have the complete system there. You can put them together, but you still need to validate via PT. But we'll talk about that. So traceability guidelines, look at people's scopes. That's why people are accredited. Here it's we upped our capability to 0.03%. Again, that's something we did. It's our uncertainty is 0.025. Our CMC is 0.03. That included test instruments and everything else under it. But The cert should state the best measurement uncertainty for different ranges. On this cert, best measurement uncertainty is 0.003 for torque calibrations from 1 to 2,000 newton meters. So we're showing. So if you want something, you want to make conformity assessments, you want something known, really critical application, this is probably the best. PTV is the best. This is second best if you need that high precision. So talked about it. Typical uncertainties. This is for force. This does not do torque, so we stuck the force uncertainties in. This is 4 to 5. Heather said at the beginning we're doing dead weight. Accredited cal suppliers 1. Torque, obviously this is much larger. Your typical is 003 to start, and then most are at 02 and 0.5, and then the actual measurement on the torque wrench for K equals 1 still is 0.5 to 2% usually, depending on the wrench. Measurement uncertainty. All measurements are subject to uncertainty, and the measurement value is only complete if accompanied by a statement of associated uncertainty. Uncertainty is a measure of how close a particular test result, the product of one laboratory, is to the true value. Really what we're saying in that force graph in this one, the further away calibration by primary standards, the larger the overall uncertainty will become. The next step here, written description of prescribed course of action or processes. If we're looking at documented procedure, the laboratory shall use the appropriate methods and procedures for all tests and calibrations within its scope. My favorite one here is measurement assurance. This is what you do, right? Practice is put in place to monitor a testing or calibration process and to ensure the calibration status of equipment, reference standards, and reference material used in a measurement process. This is SPC, statistical process control. This is maybe sending a check standard, sending a check force, sending a check torque standard to a company. They do the cal. Now I use that check standard to monitor my process. I know what the answer should be. They told me what it should be. I tweak my setup, and then I continually keep testing that machine with a statistical process, that arm. I continually keep testing it with statistical process controls in place. That way I can see if things are drifting out. I can see if maybe a new technician, I can use that to train the new technician. Do they have it? Do they have the technical competence? And speaking of technical competence, the ability of a person to do their job comparatively and on the same level other professionals in the field. Have they been trained? Nothing's really better than at the end of the day, you train somebody for all this stuff, and then you give them that gold reference that all your other techs, that the numbers are really good, nicely grouped together, and now this technician is going to go with a gold reference, one that's just known just phenomenally well. And here the laboratory shall ensure competence of all those who operate specific equipment, perform tests and or calibrations, evaluate results, and sign test reports and calibration certificates. So a way to demonstrate it is to have that cell do inter-laboratory comparisons. Also, proficiency tests. Here is a proficiency test. This is back to that E28 committee that went around. Here's our machine. This cell right here went to PTB, and we had a proficiency test. I'm going to blow up the results if you can't read them right now, but I'm going to blow them up in the next slide. But proficiency test determines the performance of an individual laboratory for specific tests or measurements and is used to monitor the laboratory's continuing performance. When you look at these, you see things like EN ratio and Z-score. A Z-score indicates how many standard deviations an element is from the mean, and then the EN is comparing the lab to the reference using this formula with expanded uncertainties. And when we blow this up, you can see really, really good scores. Typically, you want your EN ratio to be under 1. In this scenario, you can see our highest EN ratio this was a 2,000 pound inch cell that went to PTB. PTB was the pivot lab. This shows us that we have really, really great agreement with PTB. And for those that answered the question, yes, this is Morehouse, like I said, the whole thing. We can calibrate your torque cells, which can quantify any additional errors in your system. You can see here, you can run your own ILCs against like a really, really well-known cell calibrated in that machine. And you can see how you're doing. If you run your own ILCs, we have a downloadable CMC calculation sheet that allows you to run ENs. If you can run your own and see exactly where you are and what you need to improve. If your EN is over 1, You can decide to do things such as raise your uncertainty. You can decide to do things like support your arm. Maybe buy additional arms. Maybe you're using an arm that's too heavy and introducing bending effects. So, and then we get to the realization of SI units of mass, length, and time, and CIP and BIP. 1 Newton is the force required to accelerate 1 kilogram to 1 meter per second in a vacuum. And the kilograms redefined, as you know, with the SI enriched, the cool SI enriched spheres that you can look up. And then you have periodic recalibration. One of the reasons why we're in business is calibration intervals or process controls shall be established for measuring test equipment that are included in the calibration system to monitor and maintain equipment performance to the stated application requirements. So have your equipment calibrated, calculate, is it drifting out, monitor that, use control charts if you can, get that test cell, that check standard, 5-in-1 kit, some people call them, or we've called them that, where you can, do 5 things with one. You can satisfy a lot of the criteria for ISO IEC 17025. And now we're kind of wrapping up. And I'm going to talk about our standard and a little bit more for those that, have been talking about it. Here's what it is. Look at that. It's carbon fiber arms. It's a 2 kilonewton lever deadweight machine. Realized uncertainty of 0.002, which translates to a CMC of 0.003. We said 0.0025 a lot of times. That's the accreditation requirements. And when we start looking at calibration process uncertainty, when we involve all the technicians and everybody else, it raises it a hair. This is a vertical design, pure torque generated via identical weight sacks located at either end of the lever beam. Twin beam carbon fiber arm mounted on a central air bearing. We can do calibrations, in a BS 782. It did come from NPL, and we can do ASTM E28 or ASTM E2428. We purchased this machine in 2009 from NPL. Began construction of a laboratory. We became accredited around 2010. NPL sent a team of engineers. We did an originally proficiency test between the machine with artifacts that they gave us. They have artifacts with years and years of history. We have those artifacts, and we basically took the artifacts before they tore it down, took the artifacts after they set it back up, and we were operating. And then we did the proficiency test. You're supposed to have a proficiency test plan for every 4 years. In 2015, we did the proficiency test again with NMI, PTB, and several others in the committee. And I showed you the ratios of all them. And this is a primary torque standard. It was used and registered with the BIPM as a national standard for the United Kingdom. So really hard to do that. We tried to get designated here with NIST. NIST does not like to designate anyone. That would make us the primary standard for all of North America, designated by NIST to do torque cals that they do not do. However, that did not go through. It kind of left in a holding pattern where no one said yes or no. So offering, how can we help solve problems? Offering torque calibrations with low uncertainties, providing torque cells. We can do that for SBC, setup and system errors, and satisfy ILC and PT requirements. So with that, I feel we're in a position here, hopefully those that are doing this, we're in a position where we can really help get you the answer so you can go back and dissect your systems. So we're going to open it up for questions. The other thing, some other announcements, if you follow us on social media, we've been posting some cartoons, some other things. We had pretty much a jab at World Meteorology Day, and we'll have another funny cartoon for World Metrology Day, which is coming up May 20th. Announcements are done through social media for upcoming training. Our next one is a load cell troubleshooting webinar. And if you just subscribe to it, Heather sends out a newsletter once a month. We are under the firm belief that we want to pack that with content that will help make all of you better, right? Tips, tricks, things like, setup reductions to reduce time, proper adapters to make sure you're not generating, errors and passing them to the consumer. That's that metrological traceability. If you don't do things properly and get contract review properly, then you could be thinking you're giving your customers X when you're really giving them those high errors. Hopefully you're not giving them those high errors such as that, 30-some% error we showed, from not having the system parallel. But with that, I think we're going to end the recording. If anybody wants to watch that, Heather will send that out later, and we'll answer the individual questions that may or may not have